Um, Hi everyone, welcome to the CERN Theory Colloquium. We are very happy to have today Abraham Loeb, known to Avi, as Avi to colleagues and friends. He is, let me introduce him. And he's a Frank Baird Junior Professor of Science at Harvard University. He received PhD in physics from Hebrew University of Jerusalem, then moved as a long-term member to the Institute of Advanced Study at Princeton, and then in 1993 moved to Harvard as an assistant professor and quickly assistant professor in the Department of Astronomy and quickly become permanent. Avi wrote 8 books and over 800 papers on a wide range of research areas in astrophysics and cosmology, including the first stars, the formation and evolution of black holes, search for extraterrestrial life, and exploration of the outer solar system with fast and small sailcrafts, gravitational lensing by planets, future of the universe, and many more. I hope we will hear some of it today. For about 10 years, he had been chair of Harvard's Department of Astronomy. He is a founding director of multidisciplinary Black Hole Initiative, director of the Institute for the Theory and Computation. He also serves on many boards and societies. He also is a chair of the advisory committee for the Breakthrough Starshot Initiative, as well as Science Theory Director for all initiatives of the Breakthrough Prize Foundation. Finally, and maybe what is particularly relevant for today's topic, in 2012, Time magazine selected Avi as one of the 25 most influential people in outer space. So thank you very much, Avi, for joining us today, and please go ahead.
Thank you, Sasha, for the wonderful introduction. I should say that all these labels that I acquired over the years are not very significant to me, as you will understand later. I'm the same kid that I was 50 years ago, and I regard it a great privilege to be a scientist and follow my childhood curiosity. These labels are just completely secondary. The other thing I wanted to say is it's a great privilege to join you at CERN, and I would have been delighted to actually visit you in person, and I hope to do so in the future. What I will describe today is a subject I worked on over the past few years. I asked Sasha whether he wants me to speak about black holes, and he said, no, speak about this subject, because it's different. And if I will focus on a new book that just came out a couple of months ago, which you see in the middle of the slide, called Extraterrestrial. In 2 months, there will be another book, a textbook, 1,000 pages long, that is depicted on the right side here. You can see it's called Life in the Cosmos. And that would be a textbook on the search for life, both primitive and intelligent. And I hope it will be used by the scientific community in future research, because this is one of the most exciting frontiers that awaits us. And it's quite likely that within our lifetime, we will find evidence, direct evidence for life out there. And if I had to summarize my book in the middle, the one that was published, with one sentence, I would say the following: when you are not ready to find exceptional things, you will never discover them. This was the subject of a Scientific American essay that I published about 6 months ago. And what you see on the left is a photograph of a picture that was hung on the wall of the Berlin Brandenburg Academy of Science and Humanities in October 2020. It was taken by the German photographer Herlinda Quilbel, who came to my office and asked me to write on the palm of my hand the most important question that I'm curious about as a scientist. And I wrote, are we alone? Now, you might ask, when could have life started in the universe? I mean, we can search for it locally in the Milky Way galaxy, but it's also interesting, cosmologically speaking, to ask when could it have started, because the sun is a relative latecomer. Most of the stars formed before the sun. We know the star formation history of the universe, and most stars were billions of years prior to the formation of the sun. Therefore, if they follow the similar history, and they have, we know that about half of the sun-like stars have a planet the size of the Earth, roughly at the same separation, then life, as we find here, could have existed billions of years ago in the universe. But how early could it have started? Turns out the universe had room temperature. The cosmic microwave background had the same temperatures you have in your room at a redshift of 110, about 15 million years after the Big Bang. And so back then, if we existed, life could have been everywhere. You didn't need to be close to a star in order to keep yourself warm. But there were no stars at that time, 15 million years after the Big Bang. The first stars formed about 50 million years later. And so the bottleneck was not so much surface temperature as it is today. If you move away from the sun to great distances, a planet like the Earth would freeze and life would not be possible because it's based on liquid water. The bottleneck back then was not the temperature, but was the heavy elements. They were produced in the interiors of stars 50 million years later, and not in the Big Bang, unfortunately. So when did life actually start around these stars? Well, we don't know, but we can search for biosignatures, evidence for molecules that are indicative of life, in the atmospheres of planets around the oldest stars in the Milky Way galaxy. And these are called carbon-enhanced metal-poor stars. They don't have heavy elements much, so they are metal-poor. Anything heavier than helium is called a metal in astrophysics. And they are carbon-enhanced, so if they have any planets around them, these must be carbon planets. They are made of carbon, and they provide excellent foundation for life, actually, such planets. And we can search for planets around those old stars, the oldest that we know about in the halo of the Milky Way, and look for transits where we can actually infer the composition of the atmosphere of the planets from the light that passes through the atmosphere. You can see that on the right in this cartoon. Now we can look at the global history of the universe, and that's what's shown in this figure here at the bottom. And it really depends on what we assume about the possibility of life, whether it could form near stars with a mass similar to the sun, or stars with lower masses, like the most abundant stars. The nearest star is Proxima Centauri. It's 12% the mass of the sun. So if life is possible around dwarf stars, these stars would live for trillions of years, much longer than the sun. You can think of a star as a nuclear reactor, and low mass stars burn their nuclear fuel much more slowly. They can live 1,000 times longer than the sun. So what you see in the plot at the bottom, if we assume that only sun-like stars allow for life, then right now is the time when life is most likely, because the sun is roughly at the middle of its life, and many sun-like stars already finished their life. So that's shown as one of the, you can see at the bottom right, the mass of the star in units of solar masses. So if you restrict your attention to stars of order the mass of the sun, then currently is, so we should not be surprised that we live right now. But if life is possible around low mass stars, it will be most likely in the future, trillions of years from now. And eventually life will end, because, well, if the universe continues to accelerate the way we see it now, because it will get extremely cold, and eventually all these stars, even the low mass stars, will burn out in about 10 trillion years. There wouldn't be any heat source to keep yourself warm, except of course for artificial nuclear reactors that we can build. What is shown on the diagram on the left is the fact that we will be left on our own in the accelerating universe, surrounded by vacuum. So the future is quite depressing, cosmologically speaking. But let me start from the biggest lesson that I learned from astronomy over the past few decades, which is a sense of modesty. And I would like to read the excerpt of 2 paragraphs from my book that explains this perspective that I have. And it followed after both my parents passed away over the past few years. My father, David, was laid to rest in the same red soil in which he planted trees all his life, in the vicinity of those plantations that he watered routinely, near the house that he built with his rugged hands and that I grew up in, surrounded by the people he loved and who loved him in return, under the blue sky that I study as an astronomer. My mother, Sarah, who put me on the road to thinking as a philosopher, with whom I spoke daily throughout my adulthood, and who especially gifted me with a life of the mind, was buried beside him 2 years later. In astronomy, we realize that matter takes new forms over time. The matter we are made of was produced in the hearts of massive stars that exploded. It assembled to make the earth that nourishes plants that feed our bodies. What are we then, if not just fleeting shapes taken by a few specks of material for a brief moment in cosmic history on the surface of one planet out of so many? We are insignificant, not just because the cosmos is so vast, but also because we ourselves are so tiny. Each of us is merely a transient structure that comes and goes, recorded in the minds of other transient structures. And that is all. And so the sense that I get from practicing astronomy is that of cosmic modesty. And what I have a hard time understanding is how come some people, like this emperor that is shown in this picture here, were so proud of themselves. You can see him standing, being quite arrogant. Probably a lot of people bowed to this person. And if you just think about it, as I mentioned, we now know from the Kepler satellite that a substantial fraction of other, a third to a half of all the sun-like stars have an Earth-sized planet roughly at the same separation. And so not only we are not at the center of the universe as advocated by the Greek philosopher Aristotle, and since that was flattering the ego of many people, then for 1,000 years people believed that. But not only that we are not at the center, which was demonstrated by Galileo and Copernicus, we are also, our neighborhood is not special or privileged in any way, because we see billions of other systems of Earth and Sun. And if you arrange for similar circumstances, you might as well get similar outcomes. There are more habitable Earths in the observable volume of the universe than there are grains of sand on all beaches on Earth. So if you think about this emperor conquering a piece of land, it's not very different from an ant that hugs a single grain of sand on the landscape of a huge beach. That's not very impressive. But I can understand where it comes from. When I looked at my daughters when they were young, they tended to think that they are the smartest in the world, that they are at the center of the universe, just like humans did in ancient history. And that perspective changed when they went to the kindergarten and met other kids. And so our civilization will mature once we leave home and meet others. And we are probably not the sharpest cookies in the jar. And by the jar, what I mean here is the Milky Way galaxy, for example. The reason I don't think that we are the smartest kid on the block is by watching the daily news. We are wasting a lot of resources on fighting each other rather than cooperating towards a better future. And working towards a better future is a sign of intelligence. Now, Earth is our home, but only for a while. There are internal threats. We see that in terms of the climate that we are modifying. There could be wars, sort of self-inflicted wounds that we cause, and political and technological catastrophes that we may bring about. The pandemic just is a wake-up call for all of us. And of course, there are external threats from asteroids. About 66 million years ago, there was a giant rock the size of Manhattan Island that approached the Earth. The dinosaurs were enjoying eating grass, and they didn't look very far into the sky. They thought, again, very highly of themselves. They had huge bodies. They were dominant relative to their environment. But the fun stopped when that rock hit the ground, and about 3/4 of all life forms on Earth went extinct. And so the ego trip of these dinosaurs was tarnished abruptly. And that's an important lesson. Even if we deflect all the rocks that are approaching us, eventually within 1 billion years, the sun will boil off all the oceans on Earth. We will have to move into space. And I actually wrote a Scientific American article talking about the Noah spaceship, basically in the spirit of the biblical story about Noah's Ark, where Noah was worried about the great flood and tried to preserve animals by putting them into an ark that he built. We can do the same thing. Currently, all our eggs are in one basket on Earth, and a single point catastrophe would basically destroy everything we hold precious. And one way to avoid that is to bring copies to other locations, sort of like the revolution that was brought about by the Gutenberg printing press, when Gutenberg made multiple copies of the Bible that enabled a revolution, because if something bad, some catastrophe happened to one copy, it wasn't that bad because there were many other duplicates. And we can reproduce what we care about here on Earth elsewhere. The simplest way to do that is, once we are able to produce synthetic life in the laboratory, we can just send a spacecraft that has a 3D printer and an artificial intelligence system that carries all the information about the genetic makings of the life forms on Earth. You don't need to load elephants or whales on an ark. You can just put the information that is encoded in their DNA. So let me say a few words about myself, which I discuss in my book as well. I was born on a farm. I'm still a farm boy in the way that I think. I'm very much connected to nature. I was born 59 years ago. You can see a picture of me at age 7 on the top left. And I used to collect eggs every afternoon. We had chicken. And you can see that in the second photo. I used to drive the tractor to the hills of the village and read the philosophy books on weekends. Philosophy was the most interesting reading for me, because it addresses the most fundamental questions that we face. But then circumstances forced me into physics and math. I was recruited to a program during my military service that allowed me to finish my PhD, and then eventually end up at Princeton after that in astrophysics. And all of this looked like an arranged marriage until I realized that astrophysics actually addresses important philosophical questions. So I'm actually married to my true love. And I'm very happy to work on important questions that matter as an astrophysicist now. And you can see on the top right, my family. I have 2 daughters and my wife, surrounded by women. And on the bottom left, you can see a picture that was taken when a black limousine parked in front of the Center for Astrophysics at Harvard. And out of it came an entrepreneur from Silicon Valley named Yuri Milner, who actually studied physics early on in his career. So he came to my office, sat on the sofa in front of me and said, Avi, would you be willing to lead a project that would develop the technology necessary to visit the nearest star within my lifetime? And I knew that the nearest star is 4.25 light years away. So it takes light 4.25 years to reach the nearest star. And only in February, a couple of months ago, the results of the 2016 elections arrived to the nearest star system. So it's really far away. And if you want to get there within 2 decades, of course, you can attempt to make Yuri live much longer. But if you want to get there in 2 decades, then you need a spacecraft that moves at 1/5 of the speed of light. And that is 1,000 times faster than any chemical rocket that we have used before. So it's a leap by a factor of 1,000, similar to the leap from the T-car that Henry Ford developed at the turn of the century, and the Sputnik, the first satellite launched to space in terms of speed. So it looked like a very challenging proposition, and I told him I need 6 months to think about it. And then we came up with my students and postdocs with one technology that can do it. And I'll discuss it in a few minutes. And what you see in the middle bottom panel is the public announcement of the project that is called Starshot. And Stephen Hawking came for the announcement. Freeman Dyson was there. So let me explain the context. Here is a diagram of the solar system. The sun is on the left, and you can see the planets next to it. At about 10 times the Earth-Sun separation, you find Saturn. And at 100 times the Earth-Sun separation, that's where the solar wind, the wind coming off the sun, is being stopped by the interstellar medium, the gas that fills in the void between stars. But that's not the end of the solar system. That's roughly where the planets reach. But the solar system goes 1,000 times farther than that. It goes out to 100,000 times the Earth-Sun separation, and most of that volume is the so-called Oort cloud that contains rocks left over from the construction project of the solar system. So you can think of them as bricks, the building blocks that were used to make the planets, that were scattered into a much bigger volume. And that volume goes out to about halfway to the nearest star. So if you think about stars, each of them having an Oort cloud, these Oort clouds are touching each other. They are sort of like densely packed billiard balls. So the interstellar medium is full of these Oort clouds grazing each other as stars pass near each other. And of course, when stars pass near each other, some of these rocks can be dislodged into interstellar space because they're very loosely bound to the star. They move at a fraction of a kilometer per second relative to the star. So the idea is to reach the nearest star, which is Proxima Centauri. It's a member of a 3-star system, the Alpha Centauri system. And this is an artist's illustration. Turns out that this star is, as I mentioned before, 12% the mass of the sun. So it's a dwarf star. It emits mostly infrared light. It's half the temperature of the sun. And therefore, if you want to keep yourself roughly at the same temperature as you find on the surface of Earth, you have to get 20 times closer to that star. Turns out there is a planet parked exactly at that distance that was discovered. it's called Proxima B. And here is an artist's illustration of that planet. It could have life on its surface. It could have liquid water on its surface, in principle. Because the planet is so close to the star, it's tidally locked, just like the moon is tidally locked. And therefore, it shows the same face to the star at all times. So there is a permanent day side and a permanent night side. And my daughters say that the highest real estate value would be in the strip that separates these two sides, where you can see the sunset forever. So if you have a house in between the permanent day side and the night side, you can just see the sunset for your entire life. Now, if there are any creatures on the day side of this planet, they must have infrared eyes. So I asked students in my freshman seminar a couple of weeks ago if they know of any animal on Earth that has infrared eyes, and one of them found an image from Googling this, an image of a shrimp that has two eyes that look like ping pong balls and connected with cords to the head of the shrimp that lives very deep undersea, so it's in the dark. And it did look like an alien, I must say, this shrimp. But you can sort of understand why nobody comes to visit us. Interstellar tourist agencies will never advertise the Earth as a desired tourist destination, because most of the stars in the Milky Way galaxy are dwarf stars, just like Proxima Centauri. And those creatures with infrared eyes would never find our tourist destinations as attractive, because we can offer them only green grass illuminated by visible light. And they are used to infrared light illuminating dark red grass. It's also possible that the advanced civilizations close themselves off and are not interested in traveling at all, just in the spirit of social distancing, except on a cosmic scale. But it doesn't mean that we cannot find evidence for them, because they must throw some trash. And just like investigative journalists that go into the trash cans of celebrities in Hollywood in order to find out about their private lives, we can do the same. So how do we reach the nearest star within 20 years? The technology is a light sail. So if you have a very thin film of material that weighs roughly a gram and is illuminated by a very powerful laser, about 100 gigawatt, for a few minutes, then it would reach the speed of light, or a fraction of the speed of light. That would take a distance which is 5 times the distance to the moon. And you can equip this light sail. It's just the concept of a sail that you find on a boat, except it's being pushed by reflecting light. You can put on it miniaturized electronics, the type that we find in cell phones, that carries a camera, navigation device, communication device, and it will weigh less than a gram. We already have that. This technology of a light sail was demonstrated by the Planetary Society. You can see that on the right panel, using sunlight. They didn't use a laser. So here is the concept. A lot of low power lasers combine their beams into a powerful beam, and it shines on a sail that is released above the atmosphere so that it doesn't encounter the friction with the atmosphere. It's released by a mother spacecraft, and then the laser beam shines for a few minutes on this gram scale sail and brings it to 1/5 of the speed of light in the direction of where Proxima Centauri will be once it gets there. It's not the direction of Proxima right now, because Proxima is moving. And so it will take 20 years to reach Proxima, in addition to the few minutes of the launch. It's a very boring journey most of the time. And then eventually, this sail will reach the Proxima B, take a photograph, and send that photograph back to Earth. And obviously, this signal will spread along the path back towards Earth and will most likely spread more than the Earth-Sun separation. So the direction where to send this signal should be just towards the Sun. But one would need a very powerful telescope to detect it. So that's another major challenge of this technology. And it would have taken a few days to reach, for example, Pluto, whereas New Horizons reached Pluto over 9.5 years. So that's a huge saving in time. We're looking at targets within the solar system, for example. But it's not just searching for primitive life. The more important question is, are we the smartest kid on the block? And a priori, I would argue, aside from looking at the morning news, I would argue that this is unlikely that we are the smartest, because if I open a recipe book, I see that out of the same ingredients, you can make very different cakes, depending on how you mix the ingredients and how much heat you apply at different times and so forth. And early Earth had some chemicals, but what's the chance that they were mixed in the optimal way to make the most intelligent form of life possible? Quite small. So if you roll the dice billions of times, I bet you that there must be civilizations much smarter than we are out there, or they were, billions of years ago. They might not be around right now. But instead of speculating, a better approach is to search. A lot of people have opinions on this matter. I think there is no need for opinions. We should just do an experimental search. Like we search for the dark matter. People have opinions. It's a WIMP, it's an axion, it's some. Fine, let's just go and do an empirical study. And frankly, we invested 1,000 times more funds, federal funds, in the search for dark matter than we did in the search for technological signatures of other civilizations. So it's about time. We have that technology. We can address this question. And the best place to search initially is in our backyard. And it turns out that the first object in our backyard near the Earth that came from outside the solar system was discovered on October 19th, 2017 by the Pan-STARRS telescope in Hawaii on the summit of Haleakala in Maui. And this object was given the name Oumuamua, which means a scout in the Hawaiian language. You can see it circled in blue in the middle of this picture, and stars appear as a series of dots because they represent multiple snapshots taken at different times, and they move on the sky relative to that object. That object is close to us. It's actually moving much faster than the stars are. And this is the trajectory that the object exhibited on the sky. If any of you is an amateur astronomer, you would know what the purple letters, the purple words in the upper right corner mean. It says solar apex. That is the direction towards which the sun is moving in the so-called local standard of rest. So the local standard of rest is the frame of reference that you get to when you average the motion of all the stars in the vicinity of the sun. It's sort of the local frame of the galaxy. And it turns out that Oumuamua was at rest in the local standard of rest. Only 1 in 500 stars is so much at rest in that frame. And you can see that it came from the direction towards which the sun is moving. So it's just like a buoy sitting at rest on the surface of the ocean. And the solar system was like a giant ship that bumped into it. Oumuamua was not moving in the local standard of rest. So that's a very peculiar fact already. And then, of course, the sun gave it a kick, a gravitational kick. You can see the orbit here. And another weird property of this object was that its brightness changed by a factor of 10 as it was tumbling over 8 hours. And the brightness stems from reflecting sunlight. We can see this object because we use the sun as a lamppost that illuminates our neighborhood. And so we see objects that are big enough to reflect enough light so that our telescopes can detect that light. But as this object was tumbling the amount of light that it reflected changed by a factor of 10. That's very extreme. Usually we see up to a factor of 3 variations for asteroids. And that meant that the geometry of this object is unusual, most likely pancake-shaped at the 91% confidence level based on a detailed analysis of this light curve. So it's a flat object, sort of like a piece of paper tumbling in the wind. And this is the trajectory starting from July 2017 at the top and ending on the left in October. And we discovered it on October 19th when it was out of the front door into the dark street, so to speak. Unfortunately, it would have been nice to detect it much earlier. I actually visited Hawaii, the same observatory on Mount Haleakala in July 2017. But back then we didn't know about it. I gave a colloquium there. Now, this object had several strange properties. It's the first interstellar object we detected, and we knew that because it moved too fast to be bound gravitationally to the sun. We didn't expect any rock to be detected by pan-stars. I wrote a paper a decade earlier forecasting how many objects should exist in interstellar space based on what we know in the solar system. And we forecasted that pan-stars will find nothing. So just the abundance of objects of its class needs to be orders of magnitude larger than we expect based on what we know in the solar system. But it also originated from the local standard of rest, and only 1 in 500 stars is so much at rest there, as I mentioned. Its brightness changed by a factor of 10. It had an extreme shape, most likely flat, pancake-like, not cigar-shaped. It released no heat, no infrared radiation. The Spitzer Space Telescope looked very deeply around it and couldn't detect any infrared emission. And that implied the size of the object was less than 200 meters, and it had to be significantly reflective because we know how much light we received from it, reflected sunlight. So we can calculate that the reflectance needed to be more than about 5 to 10%. And if this object was 20 meters in size, it should have been a perfect mirror. So it's somewhere between a size of 20 to 200 meters. And the most important anomaly about this object was that it deviated from a Keplerian orbit around the sun. There was an excess push on it, but there was no cometary tail. We couldn't see any traces of gas or dust around it. Again, the Spitzer Space Telescope searched very carefully and put very tight limits on carbon-based molecules around this object. So it was definitely not a comet. We didn't see any cometary tail. Nevertheless, it exhibited an excess push, an extra force acting on it. And to me, the only alternative to outgassing, which we didn't see, is reflection of sunlight. And so that required, in order for that push by reflecting sunlight to be effective, it required this object to be very thin, sort of like a light sail. But nature doesn't make light sails. So we submitted a paper to the Astrophysical Journal Letters and said, maybe it's artificial. That's all. The paper was accepted in a few days, but then a lot of my colleagues got upset that the paper was published. So what are the mainstream proposals as an alternative to an artificial object? One suggestion that was made was maybe it's a dust bunny, sort of a collection of dust particles like you find at home, and making a very porous cloud of dust, 100 times less dense than air. That's what you need in order for it to be lightweight enough so that by reflecting sunlight, it will be pushed at the level that we observe. But such an object will get heated by hundreds of degrees when it gets close to the sun and will not maintain its integrity. It's difficult to imagine how a cloud of dust, 100 times less dense than air, will have the material strength to withstand heating to hundreds of degrees. Then there was a suggestion maybe it's a fragment from the tidal disruption of a bigger object by a star. Well, first of all, the chance of that happening is very small. Most of the objects you will find never passed close to a star. But more importantly, tidal disruption leads to elongated shapes, not to pancake-shaped objects. Then there was a suggestion maybe it's a molecular hydrogen iceberg, just frozen, a chunk of frozen hydrogen the size of a football field. We've never seen anything like it. By the way, we've never seen anything of these proposals. So all of them contemplated something that we've never seen before. The problem with a hydrogen iceberg is it will get, of course, the advantage is you wouldn't see the cometary tail, and therefore you could get the push just like a regular comet, except hydrogen is transparent, so it will avoid the limit on any cometary tail. The problem is that hydrogen can be evaporated very easily. And so such an object would not survive travel through interstellar space. We wrote a paper about it showing that. It will absorb starlight and get evaporated. Then most recently, a few weeks ago, there was a suggestion, maybe it's a nitrogen iceberg. Just a chunk of frozen nitrogen, pure nitrogen, because you're not allowed to have any carbon-based molecules. And where do we find the pure nitrogen? Well, we find it on the surface of Pluto. There is a surface layer of nitrogen there. So the suggestion was maybe there are lots of Plutos around other stars, and the asteroids hit the surface of those Plutos and chip off chunks of frozen nitrogen. That was the suggestion. And there were 2 papers written about it. And the only problem with that proposal, and we wrote a paper that was posted on the archive just a week and a half ago, the problem is the mass budget. In order to have enough Plutos, even if you scrape off the entire nitrogen on their surfaces, which is a small fraction of their mass, you need more than the mass that you have in stars altogether in the Milky Way galaxy, because you need to supplement that nitrogen with the rock that you have on Pluto, and you need then to supplement it with the hydrogen and helium that accompany these heavy elements. You end up with 100 times more mass that you need than you have in stars. So the mass budget is a problem to this scenario. But at any event, since all of these proposals, these are, by the way, the only proposals that were put on the table, other than the artificial origin, all of them suggest something that we've never seen before. So my point is simple. If it's something that we've never seen before, we must contemplate the possibility of an artificial piece of equipment, and we should collect more data to figure out what such objects are. And we will find something new, no matter what. And so even if these are natural objects, we will learn something new about nurseries that make such, factories that make such objects that we've never thought about before. That's how science makes progress. Only if you argue, oh, it's not interesting, it's just rocks, forget about it, then we will never know. And this is the argument about the nitrogen iceberg. I will not get into all the technical details, but F star is the fraction of the heavy elements that you need to incorporate into exoplutos in order to explain the detection of Oumuamua. And you get values of F star of order unity just by counting how much mass you need. But on top of that, this proposal argued that the nitrogen iceberg would not survive more than 1 billion years in interstellar space. Therefore, you end up only with a small fraction of all the stars. Only those that were born recently could have made an object like Oumuamua, and then you miss the mark by a factor of 100 relative to the mass that you have in stars in the Milky Way galaxy. For details, you can check, this is a paper written with my student Amir Siraj, you can check the archive. So this is an excerpt from one of the early reviews of my book. It became a bestseller in several countries. It has 27 editions in 24 languages. I couldn't really understand a couple of words in this review, and I asked my daughters to explain them to me. But the way I think of Oumuamua is just like the experience you have when you go to the beach. Most of the time you see rocks that are naturally produced or seashells. But every now and then among them, you might find a plastic bottle. And it gives you the message that there is a civilization out there. It's sort of a message in a bottle situation. Now, it turns out there was another object discovered in September 2020. It was given the astronomical name 2020 SO. What you see here in this video is the orbit of this object around the Earth, not around the sun. So this object was actually moving around the Earth, and it was discovered by the same telescope, Pan-STARRS. At first, astronomers thought it must be a rock, but they noticed that it exhibited an excess push by reflecting sunlight, and it has no cometary tail, just like Oumuamua. But then they realized, oh, if you extrapolate the trajectory back in time, this object actually came from Earth. In 1966, there was a rocket booster that was launched into space as part of a lunar lander mission. And this is 2020 SO. And the reason it exhibited an excess push is because it has very thin walls. So it has a large area to mass ratio. So we know in this case that the object is artificial because we produced it. The question is, who produced Oumuamua? Now, in between the discovery of 2020 SO and Oumuamua, there was a second interstellar object discovered. It was given the name Borisov after Gennady Borisov, an amateur Russian astronomer who discovered it. And it looked just like a comet, just like the comets we have in the solar system, with small nuances. So my colleagues came and said, well, this second interstellar object looks like a comet, must be natural. Doesn't that convince you that Oumuamua was natural as well? And I said, well, if you find a plastic bottle on the beach and after that you find a lot of rocks, that doesn't make the plastic bottle a rock. Or when I met my wife on the first date, I thought that she's special. And I met a lot of people after that, and I still think that she's special. So the fundamental question is this object, Oumuamua, the first interstellar object? And by the way, it should be common because we just looked at the sky for a few years with Pan-STARRS and we found it. So there must be a lot of such objects out there. Is it natural or artificial? And we can answer this experimentally because there would be more objects detected in the future. For example, with the Vera Rubin Observatory that will come online in less than 3 years, we should be able to detect one a month. And so it's a completely scientific question to say, let's figure out what this class of objects is experimentally. This is the first time, the first opportunity we had to study interstellar objects. We didn't know that they exist before. And the best thing we can do is send a spacecraft that will cross the trajectory of one of these. If we get an alert a year in advance from Vera Rubin Observatory, then we can send a spacecraft during that year that will intercept the orbit of this object that it belongs to the same class, looks as weird as Oumuamua. And then such a spacecraft could carry a camera and take a photograph, a close-up photograph that will tell us whether it's a rock, whether it's naturally produced, or an artificial object, a piece of equipment. We sent out Voyager 1, Voyager 2, New Horizons. Why not expect others to do the same billions of years ago? A picture is worth 1,000 words. That's what they usually say, but in my case, it's worth 66,000 words, the number of words in my book. If there was a picture of Oumuamua, which we don't have, then I wouldn't need to write my book. We don't have it because a size of 100 or 200 meters at a distance of a fraction of the Earth-Sun separation is not resolvable with the telescopes we have on Earth. We have to come close to it, just like the intercept mission OSIRIS-REx that you can see in this picture, which landed on the asteroid Bennu and collected a sample that we'll bring back to Earth. Just imagine that we find a piece of equipment in space that came from outside the solar system, and we land on it. Not only that we can read the label made on planet X, but we can also perhaps import the technology back to Earth. And if it's very advanced, they might have been 1 million years ahead of us. This will give us a leap into our technological future. So it will be an extremely educational experience for us. And one of the chapters in my book is called Oumuamua's wager. Just like Pascal's wager, Blaise Pascal, the mathematician, philosopher, argued that regarding God, there are two possibilities. Either God exists or doesn't exist. But the possibility that God exists carries huge consequences. Therefore, we should consider it seriously. That was his argument. I'm not talking about God. I'm talking about Oumuamua. And if it is artificial, that carries huge consequences to our society. And so we cannot ignore that possibility. And by the way, we can look for interstellar objects not just by seeing them flying close to the sun. For example, the moon is a museum. That's one way to think about the moon, because it doesn't have an atmosphere. The Earth has an atmosphere, and the meteors that we see burn up. There are rocks usually that burn up as they enter the atmosphere. So if they are not bigger than the size of a person, nothing is left. But the moon doesn't have an atmosphere. So everything that collides with the surface of the moon is collected, sort of like a museum. It also doesn't have geological activity like the Earth does. So it doesn't mix the surface layer with the deeper interior. So if we settle on the moon, one of the scientific endeavors that we can engage in is searching the surface for interstellar objects that impacted it and putting our hands on one of them. We can search for primitive life on interstellar objects, or we can search for technological signatures. There are also objects that are trapped in the solar system. If they pass sort of close to Jupiter, the Sun and Jupiter act as a gravitational fishing net. So an object passing close to Jupiter can get a gravitational kick from Jupiter and get trapped in the solar system. And we actually wrote a few papers calculating how many trapped interstellar objects should be in the solar system, and we found quite a lot. They stay around for about 500,000 years, and there are thousands of them of the size of Oumuamua. So that's another interesting frontier to explore, looking for them and perhaps visiting them. And if we think about the time axis, you see the Big Bang on the left here, and 13.8 billion years later, here we are. We just developed our technologies over the past century or so, which is 1 part in 100 million of the lifetime of the universe. So if you think about it, we are relatively late comers. There were stars just like the sun billions of years ago, and a lot of civilizations that predated us might have perished by now. They're dead. They're not around anymore. So when we try to look for radio signals, that's just like trying to have a phone conversation. You need the counterpart to be alive. But we can't have a phone conversation with the Mayans. The Mayan culture is not around anymore. We can find evidence that it existed through archaeological digs. So we can do the same thing in space. Search for technological relics similar to the Voyager spacecrafts that we sent in space. And of course, the civilizations that may have existed near other stars depend, their qualities would depend on the properties of the star. The sun is a relatively rare star. There are stars less massive than the sun that are much more common, and then the habitable zone is closer in, and there are stars more massive and shorter lived than the sun. And then the habitable zone is farther out, depending on the surface temperature. But we can search on planets around other stars for technological signatures. For example, you can search for industrial pollution in the atmosphere. So, you know, the astronomy community is proposing the next generation telescopes that will look for signatures of biologically produced molecules in the atmospheres of planets, such as oxygen or methane and so forth. Even if we find those, it will not be obvious that these are indicative of life, because you can make these molecules by natural processes. For example, just to give you an example, the Earth, for the first half of its life, for the first 2 billion years, the Earth didn't have much oxygen in its atmosphere, even though microbes existed on the surface. So if you don't find oxygen, it doesn't tell you that life doesn't exist on that planet, because Earth is an example for half of its life. So if we find something that behaves like the early Earth, it could have microbes on its surface, but no oxygen in the atmosphere. However, if you find CFC molecules, those are the pollutants that are produced by refrigerating systems and industries here on Earth. They cannot be produced by nature. These are very complex molecules, and they have spectral signatures. We calculated it in a paper. You can search for, with the same instruments, for industrial pollution. But this subject, for some reason, doesn't get traction in the astronomy community to be part of a proposal for a future telescope. Searching for oxygen or methane is completely acceptable in the discourse, but searching for industrial pollution, that is not part of the vocabulary of those proposals. You can also search for artificial light on the night side of a planet, like city lights. You can search for beams of light sweeping across the sky, just like fast radio bursts or other transients that are associated with propulsion system of light sails, for example. And you can search for photovoltaic cells on the surface of planets. They have a reflectance that shows an edge, spectral edge, that one can search for. Interestingly, one does not need a very powerful laser in order to reach the speed of light with a light sail. You can, in principle, park light sails next to a massive star that is about to explode, like Eta Carina, for example. When the star explodes, it produces a flash of light, and that would push the sails close to the speed of light if you park them within 100 times the Earth-Sun separation, 100 astronomical units from the star. So you can think of a civilization planting those sails around a massive star, and they would wait for the explosion, just like surfers wait on the beaches of Hawaii for a giant wave that will carry them. Another way to think of this is like dandelion seeds that you see on the right here that are carried by the wind. And then, you know, once the sails move close to the speed of light, they will fill up the galaxy very quickly. So Enrico Fermi, when he was at Los Alamos, in one of the lunches, posed the question. He said, well, if there are so many civilizations out there, where is everybody? I find this question quite presumptuous, because it assumes that we deserve attention, that they would come here and have a party with us. When I met my wife, she had a lot of friends that were waiting for Prince Charming on a white horse that will come along and make them a marriage proposal. That never happened. Why should we assume that we deserve attention, that someone will come from outside and pay us special respect? we were not particularly interesting for a long time. Just over the past century or so, we produced technologies that might be of interest to anyone outside. Before that, if you think 10,000 years back, you know, we weren't that interesting. And moreover, a lot of civilizations might be short-lived. I was asked in a colloquium that I gave last week, I was asked, how long do you think our civilization will survive? And my point was, you know, you typically find yourself in the middle of your life, you know, even though you were a baby once, you know, but that's a short period of time during which you can be counted as a baby. And you can also be very old just before you die. But again, that offers a small window of opportunity. And most of the time, you're sort of around half of your lifespan. And so if you apply that to our technological civilization, you know, we have a century or two, maybe three, but that's pretty much it. Because we started just a century ago. Now, that assumes that the free will does not intervene. We could have a policy that will extend our longevity. But if you watch how we behave and how we deal with climate change, I wouldn't be optimistic that the policymakers will do the right thing at the right time. So if others, and by the way, if we found evidence for other civilizations, we can do the statistics. Suppose there were 1 billion civilizations out there. We can draw a histogram of their lifetime, just like the lifetimes of radioactive atoms. You know, we can draw a diagram and have a likelihood for us to survive different amounts of time. That would be an interesting exercise. Because if you think about it, we are made of atoms. We follow the laws of physics. Why wouldn't we consider ourselves as part of nature? And if the experiment was done 1 billion times, there is pretty good statistics that will tell us our future. But if most of them are dead because they lasted a short window of time, then looking for a radio signal is not the right approach. Waiting for them to answer Fermi's paradox is not the right approach. The right approach is doing space archaeology, looking for relics floating in space. And my hope is that by finding those relics of civilizations that perished as a result of misbehaving, climate change, wars, so forth, it would inspire us to get our act together and avoid a similar fate. Thank you.
Thank you very much, Avi, for this inspiring and imagination-provoking talk. And thank you very much. I'm sure everyone joins me in that. And now we have time for questions. So please, if you would like to ask a question, as usual, raise your hand, and then I will call your name, and we will go ahead. So Marek, please.
Hey, so thank you very much for this talk. It's been absolutely fascinating, even though the end has been, well, hopefully kind of preaching to the choir here, but I wish people would actually wake up to what's going on. Anyway, I've got a bit of a technical question. So about the using this kind of light side biotechnology, to obviously this assumes that at least this first iteration will not actually decelerate at its destination. So how would you imagine this next step would actually be handled?
Oh, so you're talking about Starshot or about?
Yes, about Starshot.
Starshot. Yeah, that's okay. So you're right. This is a rather primitive first step in the sense that you might want to land on the surface of a planet. To me, the most important thing about Starshot is demonstrating our ability to go beyond the solar system. You know, that we might find that there is traffic out there in interstellar space. It will establish us as an interstellar civilization, which is a very important milestone. You know, since the Apollo mission, there was no concept that was as inspiring as going to the moon. And I think going to the stars is even more inspiring. But in the process of developing that technology, you also allow yourself to follow objects of interest within the solar system very quickly. So to me, the high speed has a great advantage. You know, if we had such a device today, then we could have chased Oumuamua and taken a photograph of it. We could have looked for Planet 9 directly by flying near it. We could have searched for all kinds of things that we currently cannot. And it's just enabling us to do much more than we can from a distance using our telescopes. But you are right that once we accomplish that milestone, then we should start to think about how to decelerate. Now, if you are using just the light sail technology, it's not easy because what you need is a laser on the target that will slow it down. The same way that you launched it, you can just imagine a circumstance under which you will slow it down. But there are more innovative approaches. For example, if you don't require it to move as fast as a fifth of the speed of light, the slowing down is easier. In fact, it might be possible even just with a starlight. But I don't go the extra step of asking how to improve on this concept before we actually demonstrate that the challenges can be met. And I should say that there are three challenges that we are currently focusing on. One is making the laser. A second is making the sail, selecting the material and the shape of the sail such that it will ride in a stable fashion on the laser. And the third is the communication challenge. And with respect to the laser, there is one challenge that has to do with the cost. We don't want it to cost more than CERN. And that's non-trivial if you want to build a 100 gigawatt laser. It's a non-trivial constraint.
Okay, thanks. So next question, please, from Moshe. Please unmute yourself.
Yeah, shalom, Avi. Thank you very much for a very provocative talk and very inspiring. So you have an orbit for Oumuamua. Could you tell us how long ago do you think? How long did it travel to get to us? Any idea?
Yeah, so I can tell you how long it took it to traverse the Oort cloud, the solar system. It took it more than 10,000 years. That's why I think it's probably not a functional piece of equipment. Most of the artificial objects sent out to space, just like Voyager 1, Voyager 2, will become non-operational after 1 billion years. And there will be just space junk. And most likely what we will encounter will be space junk. So I don't think it was sent to spy on us because we were not that interesting 10,000 years ago. But if indeed it's a member of a population of objects, there should be a lot of them out there.
Thanks. Anton, please.
Yes, thank you for the wonderful talk. I have a comment and a question, if I may. The comment is on the Fermi paradox. That you were saying that they are not coming because we are not interesting, but they are not supposed to come because we are interesting, but because they are interested the way we do go away, right?
Yeah, if you think about us as a subject of an experiment, like trying to figure out what's happening here. But the fact is that we are just, the way I think of us is just like ants on a sidewalk. There are so many of them, but that you walk down the street, you never pay attention to any special ant because it's not different from the other ants. So the question is, what makes us special? And are we sufficiently interesting for someone to pay special attention to us? Or another possibility is, if they do pay attention, they have a way of collecting the data such that we won't notice. Which is very likely to be the case if they have advanced technologies. But as far as we are concerned, when you live in a neighborhood, the first thing to ask is who else lives in that neighborhood? Fundamentally speaking, we are born into this world like actors that are put on a stage without a script, We have no idea what is the meaning of life, why we are here, what's the bigger picture. I mean, we are, through science, we're trying to figure out what happened since the Big Bang. We don't know what happened before the Big Bang. There are lots of things we don't know. And the first thing to ask is, are there other actors on that stage that we can consult? You know, first of all, they might know what the play is about. They might be much more knowledgeable than we are. You know, just saying it's always rocks, it's never aliens, extraordinary claims require extraordinary evidence, you know, that's to me unsatisfactory, because first of all, it's not extraordinary to claim that we are duplicated. If you arrange for similar circumstances, you might get similar outcomes. That's not extraordinary. At least it's not more extraordinary than claiming the axion exists. And the second point is that, you know, extraordinary conservatism leads to extraordinary ignorance, because you think you know the answer and you are not subjecting yourself to experimental tests. And we have seen that many times in history, including the days of Galileo, when people refused to look through telescopes. You see that nowadays when many people that work on string theory or the multiverse or you know, extra dimensions, or that suggest that we live in a simulation, not only that they are not subjecting their notions to an experimental test, but they actually do not feel the need for that. It's not as if they're apologizing for not doing that. They're very happy to be in a corner where they are protected from being shown wrong. And that's, to me, a contradiction to themselves as a physicist. You know, the way I see physics is that you have to make a pledge. You make an oath that if you come up with ideas, you have to subject them to experimental testing within your lifetime.
Yeah, a bet, like, yeah, right. Right. May I ask the question, what is wrong with the search for signals? I mean, this has a long tradition, of course.
Right.
Well, what is the limitation of this? What keeps us away from this?
First of all, let me give an update, because there was a claim that was published in The Guardian in December 2020, just 4 months ago, that there was a signal detected from the direction of Proxima Centauri called BLC1. It was the first signal that passed through all the filters that the Breakthrough Listen project is having, and so they thought maybe it's an artificial signal, because it was very narrow band around a particular frequency, and I was very suspicious about it being from an alien civilization, because it didn't drift. It didn't drift the way you expect it to drift through the Doppler motion of a planet, the Doppler effect from the motion of a planet around, for example, Proxima Centauri in the habitable zone. And also the chance that the nearest star will have a living civilization that sends out radio signals is extremely small, because we transmitted such signals only for a short window of time out of the 4.5 billion years that the Earth existed. So just finding it next door is extremely unusual. At any event, there was a talk given just a couple of days ago by a member of the collaboration that said that they identified it as interference from Earth, radio interference, which is usually the contamination that you get and you have to be careful about. So the thing about searching for radio signals is that you need the counterpart to be transmitting and to be alive, the civilization to be alive. And if they live for only 10 to the minus 8 of the Hubble time, then you cut down the chance of you seeing them by a factor of 10 to the 8. That's my problem. You have to compare that with finding relics. And you know, again, I don't think we should have a prejudice or a prior on this. We should just search in both directions. We've been searching for radio signals for a while, but we covered a small fraction of parameter space. There are lots of there is a lot of freedom in selecting the frequency and the type of signal you're looking for, and in the context of technological relics, we haven't done anything yet.
Thank you.
The next question is from David.
Yes, I copy over into the chat window so that everybody can read it. The interstellar speed of this object is not very impressive. It's very close to the mean motion of material in the Milky Way in the neighborhood of the sun. It is orders of magnitude smaller than the speed of these sails that you were suggesting as a means to visit other planets. Doesn't this low speed contradict the idea of an artificial sail object being sent from a faraway civilization?
Well, actually, the speed of this object was very small, less than 2 kilometers per second in the local standard of rest, as I was explaining. And it's just the motion of the sun relative to the local standard of rest that gives us the relative speed. So the relative speed relative to the sun is just the motion of the sun relative to the local standard of rest. And indeed, we cannot associate Oumuamua for that reason with any particular star, because all the stars are moving around and this one is sitting at rest in the local standard of rest. And you may ask, why would an object be at rest? Well, if it's artificial, it could be a member of a grid, objects on a grid that are used for navigation through interstellar space if you want to know your coordinates. Or it can be used as a relay station for communication, so that you don't need to send a very powerful beacon. We have no idea what its purpose is, but as you say, it clearly was not moving fast with a purpose of visiting us. I don't think that's likely. And one other point that I should make is when astronomers search for objects, they search for objects that move roughly at a few tenths of kilometers per second, because that's the kind of objects you see most of the time. If an object were to pass at a fraction of the speed of light and was recorded on a CCD, I think the astronomers would just dismiss it. They would argue it's a cosmic ray or something else, but they would not even consider, not even report about it. So you have to understand that there is a window of reasonable motions that astronomers record and report about. And especially if you deal with small objects, you know, there may be a huge flux of small objects, smaller than the size of 100 meters or 200 meters, that are passing by and we just don't notice them because they don't reflect much sunlight. So if an object like the light sail we envision in the context of starshot, you know, just a few meters in size, is moving at a fraction of the speed of light, we would never notice it with our telescopes. But if it collides with the Earth's atmosphere, then it will burn up as a meteor. And if it's big enough, it will reach the ground and we can examine it. So we actually wrote a paper with my student about looking for subrelativistic objects entering the atmosphere of the Earth.
Thank you. The next question is from Mazan.
Igor is the name, which doesn't matter, of course. Thanks for the talk for a non-specialist. I'm just curious. I remember seeing many years ago an argument which goes like this, that any civilization should reach at some particular point the stage where it starts exploiting radio waves, electromagnetic waves in particular range, for communications intensively, and the Earth civilization reached this stage maybe in mid-20th century. And the claim was, I don't know how correct it was, that after that, and then presumably forever, this civilization will be seen by a radio telescope as an enormously bright, unnatural radio star. And we don't see any of that. Can you comment on that, please?
Sure. So that's exactly the focus of the SETI, you know, the Breakthrough Listen project, for example, looking for such signals. You can detect our civilization, perhaps with the current radio telescopes we have, out to tens of light years, not much more than that. And I wrote a paper about this 15 years ago with Matias Zaldariaga. So if you just eavesdrop on what we are producing, now, of course, when I say we are producing, I mean the radio waves we produce through TV and radio broadcasting and so forth. There are more powerful signals that one can imagine, like when Arecibo was alive, it sent transmissions that could have been seen throughout the galaxy. These are very rare. And also when there were radars during the Cold War that were looking for ballistic missiles, they were very powerful. But even them, you could see only to a distance of about 100 light years. But that's an interesting distance because, you know, we were transmitting for, as you said, about a century, and there is a bubble of radio waves around us that stretches out to 100 light years. So in principle, someone with radio telescopes similar to what we have may know about us. That was not very smart of us to send that message, because when you enter a room full of strangers, you better listen first before speaking out, because you never know if there are predators out there. And you know, if they use chemical rockets to reach back to us, it will take them 1 million years to traverse 100 light years. So maybe for 1 million years we are safe, but eventually if they want to reach us, they will get here. Now, we should continue to search for radio waves, radio signals. We don't know what is out there, and it's an exploratory, you know, project where it's sort of like a fishing expedition. You don't know which fish you will catch. But I think at the same time, it's really important to engage in space archaeology, searching for objects, physical objects that enter the solar system from outside and look weird, and then take a photograph of them. That's the first step. And then perhaps land on them.
Thank you.
Thank you. Next, Roy.
Hello. Thank you for your wonderful talk, and especially I like the picture from the kibbutz. You mentioned Oumuamua shape being, I think you mentioned pancake and something else as well. Maybe you could expand about how the shape is relevant to something being natural or artificial. And with reference to your last comment about archaeology and space archaeology, maybe you can expand about your ability to allocate shapes and something being natural or not natural, how the shape is relevant, and what is the significance of the pancake structure. Thanks.
Right. So pancake shaped is unusual. We don't see that often with an axis ratio of more than 10 in any asteroid that we have seen before. You need an axis ratio of 10 if you want to explain the change in the brightness. So it needs to be at least 10 times longer than it is wide. And so the people that suggested the hydrogen or nitrogen icebergs, they came up with a concept of a soap bar. You know, if you look at a soap, when you take a shower, it very often gets very thin. So if you imagine evaporating hydrogen or nitrogen, it might end up like a soap bar that is very flattened, pancake shape. So that was an interesting idea that came out in that context. And you know, it's a possibility. We just need to collect more data on future objects and see if they look like. We've never seen a hydrogen or a nitrogen iceberg before. But it's natural for an object that is pushed by reflecting sunlight, because you need a lot of area for its weight. So that's what a shape like a pancake gives you. And so to me, it clicked. These two facts about Oumuamua, the fact that it had a pancake shape most likely and was pushed away from the sun by an extra force, that implied to me that it might be just the reflection of sunlight. I should say also that the force acting on it declined very smoothly as inverse of distance squared. And if you have evaporation, often you get jitter because you get it in jets. If you look at those comets, they have regions on their surface where the evaporation takes place in the form of jets. And that changes their spin period very quickly, and also introduces a jitter. And also at a certain distance from the sun, the evaporation stops because water does not evaporate anymore. And it's water ice that triggers the cometary tail. And in this case of Oumuamua, there was no evidence for a sudden drop in the force acting on it beyond the distance where ice sublimates. And there was also no jitter. It was a smooth force. And that indicated to me that, it's just the reflection of sunlight that is doing it. So these are, now, of course, if you take a photograph, you can learn much more about the shape of the object. And the issue is that if you take 100 meters, divide by a fraction of an astronomical unit, the Earth-Sun separation, you get milliarc second, and that is not resolvable. That is a very small angular scale that we can't really resolve from the ground. But the trick would be to send a camera, and I don't think it would be very expensive if we decide to pursue that. Certainly, at the level of funding that was allocated to the search for dark matter or detecting gravitational waves, we should be able to make a significant progress on photographing weird objects that after we get alerts a year in advance from the Vera Rubin Observatory, LSST, as long as we decide that it's worth the effort. And I do think that the public is extremely interested in this subject. When I wrote my book, my hope was that that someone that reads it will decide to become a scientist as a result. And that's what I told my publisher. That's my hope. And then I got an email from Malawi, from a woman that said the book is great, and I want to become an astronomer as a result of reading it. And that made my day. And I invited her to visit us at Harvard and become a student here. And so to me, science is a source of inspiration, a source of excitement. It doesn't need to be boring. We don't need to search for decades for something that we don't find.
Thank you very much.
The next question is from Vladislav.
Yes, thank you also on my side for a very optimistic and positive talk. It was a pleasure to listen. However, I think the reality is a little bit more somber than that. Especially your estimates of the habitable zone are way off of what is more or less currently known. I mean, it's the situation dating back to Carl Sagan from the 70s. I mean, the thickness of the habitable zone is extremely thin, considering that you need not only just life for a few seconds, but you need, based on our earthly experience, 4 billion years of life evolution to reach intelligent society or civilization. So that would not be possible in this examples you have given, like this Proxima Centauri. I mean, this would be out of the way completely, especially if the planet is within a tidal lock, which makes the life miserable there because it's either very hot or completely cold. So only your prime state would be a possibility for any life. So I think the talk is nice, but I think a little bit unrealistic is the assumption that there were some other civilizations. We don't see anywhere near any possibility to find it, I think.
Okay, so thank you for the question. One thing that Carl Sagan didn't know that we know now is the statistics of habitable planets. And I was quoting numbers from the Kepler satellite. So the Kepler satellite, and of course now we have TESS as well. The statistics is such that somewhere between a quarter and half of all the stars similar to the sun or lower mass have a planet roughly the size of the Earth at the right separation to have liquid water on its surface. That's something that Carl Sagan didn't know. We now know it thanks to the Kepler satellite and TESS and other missions. And that is a significant fraction because you have tens of billions of stars. Now, even if you restrict your attention just to stars around the mass of the sun, similar to the sun, you still have billions of such stars. And even if you say the habitable zone is very narrowly defined, you still have hundreds of millions of planets right now sharing conditions similar to Earth. And what I was saying is that these stars, many of them, formed before the sun, and therefore what we are going through right now happened already. So if there were civilizations, they may not be around, but they predated us. And to think that we are so unique and special that there was nobody before us, I think is very arrogant. And the simplest assumption is to say we are not special. Let's be modest. Let's be humble. Let's base our statements on evidence rather than on prejudice. So I'm advocating for searching for signatures of life, either primitive life or technological life. I think that's the way to go, rather than rely on prejudice, on what someone said 20 years ago.
Thanks.
Well, this is more the facts, but perhaps I can send you some more information later on.
I'll be glad to receive it.
Thanks, everyone. Thanks, Avi, for your talk, and everyone for coming and asking questions. Unfortunately, we are out of time, so we will have to, I guess, let Avi free. And so I would like to, on behalf of everyone, thank you very much again, and it was wonderful. So thanks, everyone, for coming, and have a beautiful, good evening. Thank you.
Thank you for hosting me. It was a real pleasure to converse with you.
Thanks.
Thank you.